Differential equations, linear, nonlinear. The only thing we're worried about is they're ordinary or not. And we do the ordinary kind in this course. So ordinary means a derivative with respect to time, no spatial derivatives, or a derivative with respect to one spatial dimension, no time, etc. So those are ordinary differential equations. Existence and uniqueness, we figured out that if the Jacobian is continuous near the initial condition, that guarantees a solution exists on a small interval of time, t0 to t0 plus delta. But if the Jacobian is bounded, in particular, there's a constant L, 200, such that every entry of the Jacobian in absolute value is less than or equal to that number L for all x and Rn, then solutions exist for all t and for all initial conditions. So they're globally defined, we say. And the key thing was for a linear differential equation, the dfi dxj was just the aij entry of the A matrix, x dot equals ax. So linear systems have nice solutions. To discover the form of that solution for a linear system, we looked at the scalar case, x when x is 1 by 1, and we discovered that e to the little at times the initial condition was the solution when the initial time is 0 and the initial state is little x0. And so we fantasized, well, maybe there's a matrix version of that. And that put us on to looking at the matrix exponential. And so this is really a construct from calculus. If you don't know calculus, you can't do matrix exponentials, because you need to know the Taylor series, not the finite Taylor polynomial, but the infinite Taylor series for a function, and then you can replace x with a square matrix. And that works because you've got x squared, x cubed, x to the k, and we can define a squared, a cubed, and a to the k. And so computing that by hand in general is not very pleasant, but we're going to see that what we really want to do is understand its properties, and it's very understandable. And just to emphasize that it's a calculus thing, we have Taylor expansions for sine of x, for example, and you can define sine of a, for example. So you just plug in a times t for x, and you get the matrix sine function. So it's no longer a matrix exponential, the matrix sine function. Cosine you can do that for. Log of 1 plus x, many different functions. Now what we're not studying in this course is the convergence of a Taylor series. That's done a tiny bit in Math 115, but really just a tiny bit. It's mostly done correctly in Math 451. And the key thing is for us on the exponential function, that series converges for all x. So for the matrix exponential, it converges for all n by n matrices. The other amazing thing we discovered is that you can differentiate the power series for e to the at. And you just differentiate term by term, and you put your finger in the wind and you cross and hope that you're not breaking any calculus rules. And you have to go to Math 451 to figure out that you can differentiate term by term the series. But when you do that, you find out that you can take the a down and bring it to the front, just like with the normal exponential function applying the chain rule. And if you wanted, you can put it on the other side as well, but we don't really need to. We've only computed matrix exponential in 2 cases. If you've got a matrix with 0, 1, minus 1, 0, that's skew-symmetric matrix, its exponential is cosine sine minus sine cosine. That's a rotation matrix. And this is really important in mechanics, the relationship between exponentials of skew-symmetric matrices and rotation matrices. We won't use it a lot here. And then if the matrix is diagonal, it's very easy to do the power series because you're just squaring, raising to a power the individual terms on the diagonal, and when you add them up, you get the standard scalar exponentials on the diagonal and 0 every place else. Okay, so we haven't used it enough, the matrix exponential, that it's a friend, but we're going to start analyzing it enough that I hope it becomes a friend. So the first thing I want to do is just note that it allows us to write down in closed form the solution of a linear differential equation, a set of linear differential equations, which is what x dot equals matrix A times x is. And then we'll try to understand the properties of those solutions, and that'll be eigenvalues and eigenvectors to the rescue. So let's just get started. So I'm going to claim that phi of t defined to be e to the a t minus t0 x0 is the unique solution to the set of linear differential equations x dot equals ax, and we have some initial time t0, and the value of the state at that is x0, and this is in Rn. Okay. And we do the proof because we want to practice these properties of the matrix exponential and keep reminding ourselves what is a solution to a differential equation. So the first thing we check, could this crazy function satisfy the initial condition? I don't know. Let's just plug in t0 for t. t0 minus t0, that's 0. 0 times a matrix is 0. The exponential of the 0 matrix only has the first term, which is the identity matrix. So this equals the identity matrix times x0, which equals x0. So yeah. Satisfies the initial condition. How about the differential equation? Well, we need to calculate phi dot of t. So that's d by dt e to the a t minus t0 times x0 and one of the properties we just learned about the matrix exponentials, when we differentiate it, the a comes down and then we keep the exponential, and then the initial condition is going to be there. But there's phi of t. So we have phi dot of t equals a times phi of t. So check, satisfies the ODE. And that's it, okay? So the matrix exponential does it. And then in Julia, we can use the command it is typed, and so if we plug in an n by n matrix times a scalar, it will simply compute the matrix exponential at a being a constant and t being a constant, but we just vary t in a for loop or a comprehension, and then we get the values of that. So Julia automatically, because it's typed, knows to apply the matrix exponential, and this is, of course, very different. I'm going to keep emphasizing it. If we did broadcasting in Julia, then that would be the exponential applied to each term of the matrix. And to be even more clear, if I take the zero matrix, not theta, the n by n zero matrix, the matrix exponential of that is this. Whereas if I did broadcasting on the zero matrix, I would get ones everywhere. Okay, n by n matrix of ones everywhere. So it's not the exponential applied to the entries of the matrix. It's the power series. So it's really important to use the power series. Okay, now's probably a good time to get questions on are we believing in the existence of a matrix version of the exponential? Okay, we kind of see that it can be defined. We went through the differentiation. We'll do it again in Julia to get A times the nice formula, and that's the secret to saying that it's the solution of a linear differential equation. But the big question is, how do we analyze its properties? Okay. Because we don't want to compute it very often. Okay. And the answer is yes, as you can imagine, because I wouldn't be setting us up for failure. And the secret is eigenvalues and eigenvectors. So let's just remember what eigenvalues and eigenvectors are. So let's take A that's n by n. If AV equals lambda V, where V is not equal to the zero vector, okay. Then lambda is called an eigenvalue of A. And V is called an eigenvector associated with lambda. Okay, so calculating eigenvalues and eigenvectors is no fun, but in Julia it's a snap. We just say F equals eigen of A. And then if we do F dot values, it'll give us lambda 1, lambda n. And then F dot vectors will give us V1, V2, Vn. Okay, so yeah, 2 by 2 matrix. At the limit, a 3 by 3 matrix, we can compute eigenvalues and eigenvectors by hand, but it's a fool's errand to do it for anything larger. Okay. Now, I have an exercise for you guys. Suppose we have an eigenvector, eigenvalue pair, okay? AV equals lambda V. What is a to the k times v for k equals 1, 2, dot, 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 dot? Okay, so see if you can work that out in 2 minutes or less. You might start with k equals 2 to get yourself on a roll. K equals 1 is easy. It's lambda v, okay? Got an answer online yet? You guys tend to be fast. One more minute. Okay, what'd you guys get for a squared times v? Didn't get it?
I have a guess, but I don't have like a good answer.
Okay. How about, what do you think it is?
I don't really know. I just manipulated it to divide by.
There's no division. Lambda k to the v for the whole thing. Oh my gosh. Okay. 2 people online, so I don't know what it is about being online. Induction. So the base case is just k equals 1. Right? So that's obvious. Let's do the induction step. A to the k plus 1 times v is A times A to the K times V. The induction says that's lambda K times lambda to the power K times V. So this is A lambda to the K times V. Lambda is just a constant. So this is lambda to the K A times V. Now it's lambda to the K times lambda V. And that's the result, lambda to the K plus 1 times V. Too easy, huh? No wonder you guys couldn't do it. You just had to multiply. And, you know, if you want to, we'll get that little thing up there in a second, but A squared times V is A times AV, A times lambda V equals lambda, AV equals lambda, lambda V equals lambda squared V. So as you take the V through, it just keeps turning into a lambda, and you multiply all the lambdas out, and you get lambda to the K. So the induction proof is short, but I think you really need to write out A cubed, A to the fourth, a couple times. Okay, let's get our QR code out of the way. Okay, Kane wants us to know he didn't copy off of Ash. What do you think about that, Max? You buy it? It's probably the other way around, right? Ash copied off of Kane, even though Ash put it up first. How about that, Ash? Defend yourself. True. Okay, you guys, at least you're having fun. Dropping class? No way Ash is dropping this class. Okay, everybody got it? Okay, so now we're going to do something really mind-boggling. Suppose f of x has Taylor expansion about the origin of a Taylor series, okay? Does that look familiar for Taylor expansion? You do all the derivatives at whatever point of interest, and then it's x minus the point of interest to the power k. Okay? So once again, we did that for exponential, sine, we can do it for cosine, we can do it for logarithm 1 plus x, we can do a million things, okay? So then f of a matrix A is just this. So I'm taking t equals 1 in the exponential, so. Okay, suppose we have that. When I put exponential here, all of these derivatives are 1 at the origin, and you get the really trivial thing. I'm going to do something, and I want you, my goal is that you don't believe it's magical only for the matrix exponential. It's a magical property for any function of matrices that you define on the basis of a Taylor expansion. Knowing that doesn't really help you in life, but I think it's just kind of fun. So, exercise. So given a to the k times v equals lambda to the k times v, compute f of a times v. Okay? It's your job. You've got 2 minutes. So take this power series, and if you prefer to put 1s for those derivatives, I don't care. But what do you get when you do f of a, it's an n by n matrix, and you multiply it times an eigenvector of the matrix A? Whoa, okay. One more minute. My hope is if you try to work it out, when you see the answer, it goes, oh my gosh. Do we have a guess? Give me a guess.
If you multiply it, then you get a to the k v, which is given, and you can substitute it for the k times v.
And then what does that give you at the end? What's multiplying v at the end?
It's like the summation, and then you have lambda to the k.
But what does that give you, since you know that f of x is that summation? Ooh, it's where it came from. Okay. What did this other thing say? It said, if v is an eigenvector of A with eigenvalue lambda, then v is an eigenvector of A to the k with eigenvalue lambda to the k. So you do a function of the matrix, which is a power, the eigenvector stays, and you just raise the eigenvalue to the power. What does this say? You take a power series, you plug in a matrix to it. If V is an eigenvector of A, it is also an eigenvector of f of A, and the eigenvalue is f of lambda. It's super cool, okay? And it's just because f of A times V is the sum k equals 0 to infinity f at 0 A to the k times V. And that's the sum k equals 0 to infinity f of k lambda to the k. And then I'm just going to factor the v out at the end. It's in every term. And that, by definition, is just the function at the point lambda, because lambda is just a scalar. That's the definition of the function when it has a Taylor series. Okay, so we get some cool corollaries from this. AV equals lambda V implies e to the A times V is equal to what? The function is the scalar exponential. So we get e to the lambda times V. Okay. Then if I put a t in here, that just scales A. Okay. This is e to the lambda t times V. Okay, so that gnarly matrix exponential, if we hit it on the right-hand side with an eigenvector of A, V is still an eigenvector, and the eigenvalue becomes this. So this is the scalar out front, and this is just moving around. Okay? So I have one more exercise for you. What is the solution to x dot equals ax x at t0 equals v when AV equals lambda v? Okay. I'm going to try to put everything together. So what is the solution to x dot equals ax when the initial condition is an eigenvector of A? Okay, so let's okay, e to the at x times x0 is the solution to x dot equals ax. Okay, the matrix exponential times the initial condition. The matrix exponential times an eigenvector is the scalar exponential of the eigenvalue times the eigenvector. Okay, so the answer is x of t equals e to the lambda t minus t0 times v. It's almost too simple. And it's because x of t is this big bad boy, what we don't want to compute very often. But eigenvectors play very nicely with functions that come from Taylor series. So this is lambda, and the t minus t0. Okay? Is this making a little bit of sense? Or does it just seem too hard and unusable? Be honest with me. Come on, ask some questions.
It makes sense, but I wonder how you derive, how you think of this.
How do I think of this? Yeah, that's the right question. How do I think about this? Okay, so let me do this. So I'm gonna, from now on, from here on, I'm gonna take T0 equals 0 just to make the formulas simple, okay? If you want to start at T equals 17 seconds, no problem. We just shift the clock, okay? Yeah. Let's suppose lambda is a real number. See, I kind of pulled a fast one on you because I didn't say whether lambda was real or complex or anything, but we'll come back to that. Let's keep it simple, keep it grounded. Suppose lambda is real. What does this look like? Okay. Suppose lambda is negative. Just exponentially decays, right? Oh. Well, that's cool. If the initial condition is an eigenvector and lambda is negative, it just decays, okay? Did we need to compute e to the at to know that? And the answer is no. This is where math and theory comes in, okay? So math and theory said, oh, eigenvalues and eigenvectors allow us to unlock the secrets of that matrix exponential. Lambda equals 0. So it's just a constant. And then lambda positive. Whoops, wrong direction. Let's get my axis going like this. Blows up. Okay? So just by knowing the sign of lambda, I know qualitatively what this is doing. That is extremely valuable. I did something that's, okay, it's numerically a little bit expensive to calculate eigenvalues, but it's a one command in Julia, so it's okay. It's a lot easier than computing the matrix exponential. And now I've been able to say, oh, if I take the initial condition as an eigenvector, I know exactly what's happening. What is the long-term behavior? Lambda less than 0, lambda equals 0, lambda greater than 0. So I'm revealing how I think about eigenvalues and eigenvectors for understanding solutions of linear differential equations. So when lambda is negative, this limit is 0. When lambda is 0, it's not very interesting, and it just stays constant. And when lambda is positive, that's scary. It blows up. Okay. Now, the restriction is that we're only able to do this when we have initial conditions that are eigenvectors. Okay. Suppose the eigenvalues of A are real and distinct. Okay. So I've got n eigenvalues, and lambda I is different than lambda j for I not equal to j. Okay? Then the corresponding eigenvectors so we'll have vector v1 associated with lambda 1, v2 dot dot dot, vn associated with lambda n. So these guys are eigenvectors, so they're not zero. Are linearly independent. And hence, form a basis for Rn. Now you may be rusty on your bases, and you may be rusty on linear independence, but I'll remind you very quickly, okay, once you get that written down. So things are dependent when, say, 2v1 plus 3v2 plus 7v3 minus 18v4 equals 0. So I can find non-zero coefficients, they add up, and I get 0. That's dependent, okay? Something is a basis if every vector in Rn can be written as a linear combination of those elements. So, conclusion. For all x0 in Rn, there exist coefficients alpha 1, alpha 2, alpha n, and they're reals such that x0 equals alpha 1 v1 plus alpha 2 v2 plus alpha n vn. Oh, So it's not just the initial condition equal to an eigenvector. I can take any initial condition and write it as a linear combination of eigenvectors. Okay. Hence, x of t equals e to the t x0 equals alpha 1 e to the at v1 plus alpha 2 e to the at v2 alpha n e to the at vn but the matrix exponential interacting with eigenvectors gives us beautiful things. Alpha 1 e to the lambda 1 t v1 alpha 2 e to the lambda 2t v2 alpha n e to the lambda nt vn. Okay, so here's how I think about solutions of linear differential equations. Yes, the answer is e to the at times x0. However, I almost never, ever, ever compute the matrix exponential. I compute the eigenvalues and eigenvectors of A. Why? Because then I know what the solution is. This is a linear algebra problem. Writing x0, okay, all you're doing is setting v1, v2, vn is the column of a matrix. You multiply times alpha 1, alpha 2, alpha n, and you get x0, okay? Because these are linearly independent, the determinant is not equal to 0. So that's a linear algebra problem. Getting the eigenvectors, linear algebra problem. Fact from linear algebra, the eigenvalues are distinct, which is the generic case. The eigenvectors are linearly independent. So I just express my initial condition as that, and now I know everything about the solution. Suppose lambda 1 is positive and alpha 1 is non-zero. The solution is going to blow up. It's unavoidable. It's going to blow up. Suppose this one, lambda is negative, this lambda is negative, they're all negative except the last one, and this coefficient in my initial condition is non-zero, it still blows up. Going to 0, going to 0, going to 0 plus blowing up equals blowing up, okay? If this is negative, this is negative, this is negative, all of the eigenvalues are negative, then the solution decays to 0 for any initial condition. It doesn't matter. If this is negative, I don't care what alpha is. The limit is 0, okay? V sets directions, this sets amplitude. This is amplitude, this is amplitude. So that's how I think about solutions of linear differential equations. Okay, so we'll take our pause, and then we're going to just return, go through partly what we just did again, but you've got everything right here. You now know exactly what the solution is doing, and you never even had to compute the matrix exponential. You just need to get eigenvalues and eigenvectors. You solve one set of linear equations, and then you write down the solution. That is powerful, okay? That is very powerful. You write down the solution after solving one linear equation and using the eigenvalue command in Julia. So I think you'll enjoy when we come back. So take a little break, get our brain rested a time. Okay, so these slides have the kicker, and then we can do that Julia brings partly to slide. Okay. Okay, so this is something very similar to what I've already written down. Okay, so got a linear system. You take an initial condition, being a vector in Rn, and then we assume that vector is an eigenvector. As the solution is, as we've worked it out. And then just pointing out that if you take the norm of that, it's going to 0. So before, when I was doing my little calculation, I just had e to the lambda, which was a scalar, but you know, the solution is this is e to the at times v. So when lambda is negative, goes to 0. When lambda is positive, danger, danger. And when lambda is 0, it just stays a constant at the initial condition. Nothing changes. The system is in homostasis. Okay, so stability, justice. So stability is associated with solutions that die out when they are perturbed away from an equilibrium. We'll define equilibrium formally, but for a linear system, if it starts at 0, it stays at 0. Put the 0 vector in, e to the at, whatever that is, times 0, that's 0. So it's an equilibrium. You start there, you stay there. So what we're seeing is, just by looking at the eigenvalues, we know something about whether a particular solution, when it's an eigenvector, is asymptotically decaying or it's blowing up. Now, we're not talking here about oscillations, and we'll see how oscillations arise. This is that fact from linear algebra we just mentioned. It's not obvious why you need the eigenvalues to be distinct until you go through the proofs, okay? And then you look at counterexamples and stuff. Take a random matrix, you compute its eigenvalues, you're not going to have two of them the same. So it's a pretty generic situation. And when the eigenvalues are distinct, the eigenvectors are automatically linearly independent. So it's kind of a big thing that we don't spend enough time on in Robotics. It's in the appendix of the textbook. I'll look through with the proof that shows that. Okay. That's where being able to use the eigenvectors as a basis for RMs. We take our arbitrary initial condition now, we just write it out in a new basis. The reason one uses one basis versus another in a vector space is certain calculations are easier in one and the others are easier in another. You guys in Rob 101 got pretty good at taking a set of vectors and then using Gram-Schmidt to make an orthonormal basis, for example. Yes. And then from that, you built the QR factorization of the matrix. So you've already seen that choosing bases can help you
if the selection is done wisely. Here, the wise choice, it turns out, is to use the eigenvectors of the matrix A in the differential equation. Because once you do that, everything looks like scalar. All of that is a scalar times one eigenvector. Another scalar times a second eigenvector plus the scalar times the last eigenvector. So it's straightforward to understand what's happening to each block. So it's just a vector sum of ordinary scalar exponentials. So I should even emphasize. So this complicated thing, e to the at, we take it all apart by using eigenvalues and eigenvectors. Break it down into something that we can wrap our head around. That's the intuition. That's the thing you can see. We can see this blowing up when lambda is positive, and we can see it decaying when lambda is negative. Okay, so if that's the solution, I get rid of the answer. Question: when is it true that the solution of a linear differential equation will decay to zero for an arbitrary initial condition Rn? When is it true that no matter where I start, all the solutions go back to the origin? The answer is, well, if x is arbitrary, then these coefficients are arbitrary. If lambdas are all negative, then we don't care what the coefficients are. Everything is going to zero. But if one of the lambdas is positive, it'll blow up, and so all I need is to take an initial condition that has this coefficient non-zero and it blows up. But even if lambda is zero, this is a constant. If this is not zero, the solution is not decaying to the origin. So this is a very deep qualitative statement. All of the solutions of x dot equals ax decay to the origin if and only if all of the eigenvalues are negative.
Okay.
That's a huge statement. It's a very powerful statement. So Justin, your segue is stable. It's upright, it gets perturbed, it will return to the upright position. If and only if, write down the model, look at the A matrix, x dot equals ax, and calculate the eigenvalues they need to be negative. And then the y is if you have anyone that's not positive, just take that initial condition. It's not going to zero. Okay. Under what condition can I find an initial condition such that the norm of my solution explodes to infinity? So, we pose it this way. Under what properties of x dot equals ax can nature choose an unfortunate initial condition for me such that the solution blows up?
when eigenvalue is positive.
You just need one. You don't need all. You need all to be negative to decay, but you only need one bad apple to ruin the whole bunch, okay? That's the way to remember. One bad apple ruins the whole bunch. One positive eigenvalue. You just need one. Okay? And then if it's positive, yeah, if it's strictly greater than 0, take that as an initial condition. But if you take any initial condition, so almost every initial condition, okay? Suppose this one is positive, but all the others is negative. We don't care what those numbers are, as long as this one is not 0. And if I just randomly choose an initial condition, that's going to be uniformly distributed, the alpha 1, so it's not 0 very often, okay? So, and yeah, so I'm getting too excited. And if lambda is positive, what initial condition make this happen? And you take any this with the corresponding coefficient positive, then it blows up. It doesn't matter that all the others are negative, positive, just don't care. Is that awesome? You're not sure yet. Okay, not sure. You're true your homework aid, but we'll come back to this. Let's play around with some trivia examples. Then we'll come back to this. Just like Colonel died out. Colonel is ready! Oh yeah, baby! I'm excited. I've got a live Colonel. You're going to share in that excitement, I hope, right? Yes. Okay. So reviewing some of the stuff, okay? Let's look at the derivative of e to the at is a times e to the at, because that is the crucial component that makes the matrix exponential the solution of x dot equals bx. And so what I've got here is a simple function that does a Taylor polynomial. I can't go out to infinity. I don't think my kernel wasn't alive. Oh, it did. Checked. So I calculate e to the at, so it's got I plus at squared up to, here I use n equals 5. So it's just a polynomial, and I differentiate that. And so I differentiate the I get 0, I differentiate the at, I get a, I differentiate a squared t squared over 2 factorial, and I just get t, etc. Here I take e to the at and I multiply it by a, and then I compare and see that I get the same thing. And Julia's got a squared term, the cubed term, the fifth term, sixth term, and then the fourth term is at the end. That's why it says here. They're not in the human-centric order, but it still is the same polynomial. Okay, that's just what the symbolic likes did. Anyway, see you later. I'm going to do it in a different way. Okay, so d by dt of e to the at is the same thing as a times e to t. That gives us the explicit solution to x dot equals ax as being this monstrous matrix, n by n matrix of functions. So, no, we agree that is complicated. And here what I'm going to do is just compare the analytical solution to the differential equation solver. So I got my linear system. And then I'm just doing the Julia exp of AT for discrete t's. And so the blue line is the e to the AT times x0, and the orange line, brown line, that's me doing e to the AT and Julia multiplying it for you guys over here on the left, and then plotting x1, x2, x3, x1.
Okay.
So, if you believe the solver, then you have to buy into the fact that, the analytical solution, so this is just using the Julia exponential function, t minus t0 times x0. And then this is like a comprehension. It's a for loop in one line. It's just calculating the analytical solution for t and the height that we set up to get at 200 volts. Okay, we mentioned eigenvalues. This is how we compute them in Julia. F equals 9 is a displayed F. Okay. Now, eigenvalues can be real and they can be imaginary. So we'll talk about the imaginary case a little bit, but mostly you'll explore this in Julia homework 8. That's why you can't drop it. It also does the Laplace transform. But remember Euler's formula. E to the I theta is equal to cosine theta plus I sine theta. E to the I omega t is cosine omega t plus I sine omega t. Complex eigenvalues will give rise to oscillations in the solution. So you guys know, I think physically, if I take a spring and put a mass on it, it's going to oscillate. And if I put friction on it so the mass is sliding against the wall or it's doing this, then it dies out while oscillating. Okay. And if I could put in negative damping, so when it slides, it adds energy instead of subtracting energy, then it would go like this and explode while oscillating, okay? All of that can be seen in the eigenvalues as well. So that's what Julia homework 8.
See?
The real part being positive is a problem because e to the a plus I omega, little exponential, is e to the a times e to the I omega. Now we add the t's in, e to the at, if that's positive, that blows up. Well, e to the minus, e to the I omega oscillates. And so this is a problem, as you'll see in homework 8. Now this is a real eigenvalue. We know what that one's doing. If we take that as the initial condition, it should die out. And if I take this as an initial condition, it should explode. I'll have that set up in the next one. All right, okay, so got an A matrix in here, it's basically random. I'm computing the eigenvalues, okay? There they are. And I'm going to take an eigenvector that corresponds to this eigenvalue. So we expect the solution to there's every single component of the solution. First component, the second component, the third component, the fourth component. Now, if I take this as the initial condition, it shouldn't be so nice, right? So I'm going to change it to the second eigenvector. The real is because when Julia calculates the eigenvalues and eigenvalues, it calls them complex type. I want to get rid of this 0 on the imaginary, so I'm just doing the real part. And the same thing on the eigenvector. So this is a complex eigenvector in Julia, even though this imaginary part is 0. If I want only the imaginary part, like on these, then I say IMAG, imag. Okay, so I just changed this to 2, and it's not happening. Everything's blowing up. Did I compute e to the AT? No. I rarely do that.
Got it.
I use my EX215 to get my RLC circuit model. I use my ME240 to get my mechanical model. I use Lagrangian dynamics to get my models. I go to ME and I use my thermodynamics and I get my model. I take chemistry and I use my first order, second order reactions and I get my models. And when it's a linear model, I write the differential equations as couplings first order, x dot equals ax. And then, yes, I know the solution is e to the at times the initial condition, but I use that fact to analyze what the solutions are going to do. I rarely compute a solution now. I look at eigenvalues and eigenvectors, and by looking at these numbers, it turns out it's only the real parts because, yes, this oscillates, but the fact that this is positive is bad, okay? Where if it were negative and dying out like a damped blocks, then it's good. It's the same thing on Justin's segways. When it gets pushed, if it oscillates a tiny bit while dying out, the rider is not going to get seasick on it. But if it does this, it's throwing all the cargo off. Okay? So eigenvalues tell you the qualitative properties of the solutions. And then, back to here, when we just took a random initial condition, well, almost certainly it has a component that's in the direction of the eigenvector that has a positive eigenvalue. So that's why things are getting very big.
Exactly.
And it's the complex part of that that's causing oscillations. I let it simulate further. This is unstable. And I just took a random initial condition. It's because, yeah, it wasn't just lying in this direction. That's the only direction the eigenvector associated with this eigenvalue will give me a bounded solution. But everything else is going to blow up. We're good? Eigenvalues, eigenvectors, that's why we want to work with it. Okay, so I'm just going to go through this very quickly. What makes this a little bit more complicated is yes, use complex arithmetic, okay? And at your stage, you haven't done a lot of it. Once you take each 215, you'll do a lot more, okay? Take a circuits course. But the eigenvalue you can write as a real part plus an imaginary part. The eigenvector, you can do the same thing. It can be decomposed into real parts and imaginary parts. You've got Euler's formula, and then this e to the ATV, it doesn't care whether the eigenvector is complex or not. We just did that calculation, and if AV equals lambda v, it's still lambda to the k when you apply it to a to the k, so it's the same thing. And so you just have to write down what this are. Now this is really important, this scalar term. It's called a complex exponential. Exponential, when there's a sum in the exponent, is the product of the exponentials. So this is e to the AT times e to the I omega t. And that's where you get the e to the AT cosine and e to the AT sine. And this has a real and imaginary part, this has a real and imaginary part, and you can calculate the real and imaginary parts, and that's what they look like. And this is stuff that will be helpful when you get into homework aids. So I'll let you either read it in the textbook or come back here, and there's a lot of stuff in the markdown boxes to help you understand. But what this formula is saying is the following. The imaginary part of a vector, that's a real vector. Take a real vector plus I times a real vector, that's a complex vector. The imaginary part is what multiplies the I, the unit, the imaginary unit. So this is real. E to the AT is real, so the whole thing has to be real. Now, you work that out, and what you see is you get e to the AT cosine omega t times the imaginary part of this vector. But you also get a term times the real part. You've got to grind through the calculations to see it. But what it says is if you initialize with anything, that's a linear combination of either the real part of the vector or the imaginary part. It evolves in a two-dimensional subspace in Rn. Vi and Vr are two linearly independent vectors. They give you a two-dimensional subspace in Rn. And the solution is oscillating with this frequency. It's expanding or contracting depending upon the sign of A. A is negative, so the eigenvalue has a negative real part. This goes away. And you got stability. That's what allows you to understand how to choose real initial conditions. Because you're saying, I can't initialize my RLC circuit with a complex eigenvectors. What do I care about complex eigenvalues and complex eigenvectors? Well, you can initialize it with the real and imaginary part of that eigenvector. And you see exactly the same behavior as we saw in the real usage. So you've got oscillations. You still have the real part determining expansion or contraction. And it's times components of the eigenvector. Are our minds blown? Are they, has the ground been plowed enough that the seeds, when you read the book and do the homework assignments, will grow and you'll understand something? You got questions? And, okay, so there's some more stuff there. So I think I'm going to do a little go back to Julia. So this is just solutions of linear differential equations.
Jill, why don't you do that? Oh, okay. Okay.
Working just a few minutes. So then let me write it out.
Back to here.
Linear approximations of linear t's. X dot equals x with x, x0. We've seen that if that right-hand side were linear, then we know a lot about the solution. We just calculate eigenvalues. Necessary eigenvalues, mostly the eigenvalues of what we're after. So when it's nonlinear, what can we do to help understand this better? So in equilibrium is when S at E equals 0 means solution from XE is constant vector. Those are used to these. Okay.
Yes. Energy.
Sorry. Here's a pendulum. It'll measure theta from the vertical in the downward position. So this is theta E equals 0. This is theta E equals plus minus pi into that. So you recognize that as being an equilibrium of a temp. So, roots of the right-hand side of a differential equation are called equilibrium. So you just solve f of x equals 0. Those are called equilibrium. Okay.
So,
I take f with equilibrium. That's term. This is the part that was messed up. So this is just the linearization of a nonlinear function about a point. That's equilibrium, that's 0. This is just a constant matrix. So you should call it officially, delta x is x minus xc is our perturbation from equilibrium. Delta x dot is a times delta x. It's just a linear approximation. X dot equals f of x near the equilibrium x. Okay, so if we have equilibrium, we can approximate the nonlinear system this is a linear ODE. And we'll find out if you guys are glass half full or glass half empty. Okay. It's like, can this linear differential equation, this small signal approximation, delta x is a small deviation away. That's when this part is a good representation of the nonlinear thing. Can that tell us anything about the actual nonlinear system? And the answer is yes, okay? Yes. All I'm going to abbreviate Eigenvalues. Okay. Now, get into real parts. Notice where x zeros sufficiently close. The equilibrium xe, the solution of the nonlinear ODE decays back to the equilibrium. Great. So this is proven in EECS 562. It's certainly not easy to prove. That's why it's an undergraduate course. But I would say 80% of technology is based upon this one fact alone. Okay. There's almost not a single linear system out there. They all have nonlinearities. And even if you do your simple RLC, let me put a mega amp through that resistor and you tell me what happens to it, okay? Oh, it's not linear anymore, is it, okay? Let me take a mass and try to accelerate it to the speed of light. Son of a gun, that doesn't work. It takes infinite energy, and we need Lorentz transformations and all this kind of stuff. Son of a gun, it's not linear. Friction tends to be, air friction is v squared, so it's not linear. There's all sorts of nonlinear sines, cosines, and or robot arms. Okay? However, we do a linear approximation of that differential equation. And the linear system has all eigenvalues with negative real parts. We've got these e to the a decaying things, possibly times a sine or a cosine, possibly not. All those things, all the linear deviations decay to zero. The solution of the nonlinear system returns back to its equilibrium. Adjust them, that's how your device will stay up, because it's not linear. And so, this one fact, stated more formally in the text model, that's local asymptotic stability. Okay, so what this cancels to is putting a 0 through the f of x e, and this is taking the Jacobian and putting an a over it. So f of x e is a times delta x, just like we wrote down. So we start out with this nonlinear ODE. We use NL solve to find equilibrium. We use forward diff dot Jacobian to calculate the Jacobian. We get a constant matrix, and we form our linear approximation. So here's the pendulum. Its equilibrium, as we just went through, or the velocity should be 0, and the angle can be down, and I didn't put the plus minus on here. That boy, okay. We turn the second order differential equation into first order form. There's the nonlinear pendulum. We've seen it a few times now. We calculate the Jacobian. And we get this matrix that we've seen before. 0, 1, minus 1, 0. The exponential of that times t was cosine t, sine t, minus sine t, cosine t. Oh, for you guys. Cosine t, sine t, minus sine t, cosine t, okay? So it's a rotation matrix. Things are just oscillating. The eigenvalues of that matrix here are plus minus I. And e to the I omega, e to the it is just cosine t and sine t. So that's for the downward equilibrium. It doesn't blow up, but it just oscillates. And for the upward equilibrium, there should be a problem there, right? So just see how well these linear models represent solution of the nonlinear. Yep. So in the downward equilibrium, what did I take my deviation from? I kept doing the downward equilibrium. I made it pi over 8. Should we make it pi over 4 or make it something significant? Pretty close, huh? It's surprisingly close. So when things stay bounded, the linear approximation has a chance. Here's the same example, though, for the upward equilibrium. Oh, come on. Can't work in my office and then not work here. Yes, we can. Okay. Okay, so we'll skip that, but what happens is the other one falls down and then it can come back up. The linear thing has an eigenvalue. One is plus 1 and the other one is minus 1. So it just goes. So the linear approximation deviates a lot from the actual nonlinear solution after a while. So here's an equation where you guys don't have physical intuition like you do for the pendulum. Max and trying to break your intuition. Just use analysis, right? So second order, just like we had before. To get equilibrium points, the roots of this, since you can factor out x and then you're left with a quadratic, it's easy to find the equilibrium. When you calculate the Jacobian, this is what you get. Depending upon these parameters, the eigenvalues of A can have negative real parts, they can have positive real parts, etc. Okay, so there's Jacobian with numbers. Here's the eigenvalues. The real parts are negative, so that's good. That's the decay. This is oscillation. So that's cosine almost t and sine almost t. Okay. Here's the initial condition. The dotted line is the linear solution, and the solid blue line is the actual nonlinear solution. Pretty cool. Okay? That's what happens when things are basically stable. Well, they are stable. Here's another set of parameters that are not so nice. Eigenvalues, positive real parts. That's blowing up at e to the 0.4t. So 10 seconds, that's e to the 4t. 200 result. Okay. Yeah. And notice, so here's where we started. Here's the equilibrium. The nonlinear system is not going back to the equilibrium. The linear system is deviating from it after a while. But the linear analysis tells us that we are not returning to the equilibrium. But you read the linearization of the robotic equations on your own. So this is the two-link manipulator. Trying to recognize complicated terms. There's a highly professional drawing of the various equilibria. Okay? So there's no torques anywhere. Okay. So this is the upward equilibrium. This is one of the downward equilibria. This is a third one. I could have, well, there's two more. I could have this link up and this link down. I could have this link down and then this link folded back up. Okay, those are all the possibilities and you're welcome to explore them. Okay? But I'm just going to use these two. Got some function parameters in here. Okay. Now, for this system, for the upward equilibrium, what are we predicting? We have two eigenvalues that are negative. There's one, there's actually two, but we don't care. There's one that's positive. So we're predicting that if we perturb it, it's going to do what? So fall. It's that. Now, what I'm going to do is use a technique from EECS 560, linear system course. This is called a state variable feedback. We don't do that in this course, but I'm just showing you. This gain is modifying the eigenvalues of this two-link pendulum. Notice what they are now. Real parts, negative. Real parts, negative. Yeah, we've got imaginary parts, but the real parts are all negative. This is what feedback is, but it is done. It takes eigenvalues that are not negative, they're unstable, and it makes them stable. And I simulate the nonlinear system. Yeah, the curve is. Yeah. So that's feedback.
Yeah.
So if you take EECS 460, learn about transfer functions, which we are going to start on next week. If you take EECS 560, it's differential equations in what's called state space. X dot equals AX, and you put B anywhere in this to control it. But it takes these nonlinear systems that are unstable, equilibrium, and makes them stable with feedback. And this model, if I had to design that feedback basis of all of this stuff, there's no way I could do it. But when I get to reduce it to working with linearization, then it becomes very straightforward. So linear approximations, Jacobians, are amazing. We use them for root finding. We use the Jacobian transpose for scalar function. We call that the gradient. We got gradient descent. We have constraints. We can still do gradient descent with constraints. If you have nonlinear ODEs, linearize them, you can analyze them, you can't solve them in closed form. If you want to believe the simulation, analyze the eigenvalues of the linearization around an equilibrium point and compare it to your simulation. And then what we're going to learn in chapter 10 with Laplace transforms is how to take these unstable models and stabilize them with PD controls, the easiest type of controls. But you got to start somewhere. Okay? We'll do it with PD controls, and you guys will get an idea of how engineers deal with nonlinear systems. And this is what they don't teach you in the math department. They just say, yeah, we do a linear approximation. You don't know why you care about ours. You don't know why you care. And in the math department, you'd probably be terrified of EDAT the whole time because they wouldn't do enough of the eigenvalue decomposition that makes it transparent. Yeah, you gotta dip your toes in the water, have some fun. This is really the good stuff of differential equations.